Hello, welcome again. We are solving some questions of fluid mechanics and machinery. Question number 43. The topic is hydraulic machine. Question number 43 and 45, 43 to 45 carry a common statement. The statement is the internal and external diameter of an impeller of a centrifugal pump which is running at 1000 rpm and are 200 mm and 400 mm respectively. The discharge pump is 0.04 meter cube per second and the velocity of flow is constant and is equal to 2 meter per second. The diameter of suction and delivery pipes are 150 mm and 100 mm respectively. And suction and delivery heads are 6 meter absolute and 30 meter absolute of water respectively. If the outlet vane angle is 45 degree and the power required to drive pump is 16.186 kilowatt, determine question number 43 main angles of the impeller at inlet. Option A 12.8, option B 10.8 degree, option C 7.4 degree, and option D 11.6 degree. Question number 44 is the overall efficiency of the pump. Option A 60.74%, option B 70.12%, option C 68.15%, and option D 65.12%. So and question number 45 is the manometric efficiency of the pump is 61.98%, option B 79.12%, and option C 80.12%, and option D 85.12%. So here the data given are the RPM of the turbine of the pump is RPM of the pump is 1000 rpm. Internal diameter and external diameter are 0.2 and 0.4 meter respectively. Discharge is 0.04 and velocity of flow is constant through the velocity of flow is constant and so it at inlet and outlet, so it is equal to, so vf1 is equal to vf2 is equal to 2 meter per second, and diameter of suction pipe and delivery pipe are 0.15 meter and 1 meter, and absolute head at absolute suction head is 6 meter and absolute delivery head is 30 meter. So vane angle at the outlet is 45 degrees. So power required to drive the pump is 16.186 kilowatt. So these are the data given. Okay, now this is your inlet velocity diagram. This is your u1, this is your vf1, this is your relative velocity. Okay, so this relative, so because there is no valve component at the inlet of the turbine or at the inlet of the pump, so there will be no Vw2. So V1 will be equal to Vf1. So this is your relative velocity, and this is, so this will be your relative velocity, because this is your relative velocity in vertical direction. This is the relative velocity in horizontal direction. So this will constitute a total relative velocity component, total relative velocity vector. Okay, so this angle will be your tangent theta and will be Vf1 by u1, 2 by u1, and u1 is your pi dn1 by 60. So d1 is your 0.2 meter and u1 comes out as 10.47 meter per second. So putting the value of u1 here, we get theta as 10 degree 48 minute or 10.8 degree. So answer to question number 43 is your A. Okay. So next question is overall efficiency of the pump. So overall efficiency of the pump is the power that the total head generate which is generated by the pump, that is the power WHM divided by shaft power, the power that is has been supplied to centrifugal pump. So so that W is equal to rho Qg. So overall efficiency will be rho Qg HM divided by 1000 into power, and because power is given in power required to drive the pump is given in kilowatt, so converting into watt. Okay, so overall efficiency is we can is overall efficiency will, in terms of HM, will be your 0.02424 HM. Okay, now the HM is the manometric head, and it can be found out by the difference of total head between delivery and suction. So this is your this is the for if you apply Bernoulli equation between delivery and suction. So this is the total delivery head, okay, with velocity head, and this is your total inlet head. At as the pressure at the inlet and outlet of the delivery inlet and outlet is atmospheric, so this P1 by rho g and P naught by rho g will be same, and this Z naught and Z1 are given as 30 and 6, okay, and V naught square is the velocity in suction pipe, and ds sorry, velocity in delivery pipe, and this is velocity in suction pipe, okay. So so this will be your this velocity V naught will be your q by pi by 4 d square, that diameter delivery pipe, diameter delivery pipe, and this will be q by pi by 4 into ds square, okay. So dd is your 0.1 and ds is your 0.15, okay. So hm will be your if you find out, if we put here the values, then hm will be 25.06 meters, okay. So overall efficiency will be if we put the value of hm here, then the overall efficiency will be 0.607 or 60.74%. So answer to question number 44 is 70. This. So next is manometric efficiency. So manometric efficiency is given by power that is converted in terms of manometric head. So that is the end power divided by the power imparted to runner, power imparted by the runner to the to that power imparted to runner, that is rho q bw2. That is that the pressure that that is generated to this. So that is generated by the shaft power. Okay. So that is the manometric power. So that we have HM. Okay, now we need to find out dw2 and u2. U2 we will find out by just putting the value of d2 pi d2 n by 16. Now one thing is left, so that is dw2. So this is your outer velocity diagram. Okay, so this is your v2, this is vr2, this is vf2, and this is beta. This is the horizontal component of velocity, this is the flow component of velocity, this is your u2, and this is your vr2. Okay, so this will constitute u2 minus vw2, and this is your vf2. So this is your blade angle, and blade angle at outlet is given as 45 degrees. So this tangent phi is equal to vf2 divided by u2 minus vw2. Okay, so that is tangent 45 is 1. So 20.94 minus vw2 is equal to 2, or vw2 is your 18.94 meter per second. So putting these values, we can find out manometric efficiency, that is 0.1698. That is, sorry, that is 9.81 into 25.06 divided by 18.94 divided by 20.9, or this is 61.9. So answer is that is wrong. Okay, so that is 61.98% answer.